Hello guys. So today's topic which we are gonna discuss is heaps. So we are gonna cover heaps, bottom up, and heapify with the time complexity based questions, and we are gonna cover maximum of the topics right there. So let's dive into this. So first question is they have given as an array. It is converted into max heap using bottom up algorithm. Okay. So in bottom up algorithm, we don't just sort it out by inserting each element. First, we'll draw the whole tree 82, 101, 90, 11, triple one, 75, 33, 131, 44 and 93. So which are the first three elements of the resulting heap array? Okay, fine. So first we have to consider this level, then this level, then we'll go eventually. So considering this level 93, does it have any children? No. So this is perfect heap. If there is only one element, then what would you heap it? This is the minimum, this is the maximum because it is the only element. So I hope you got the concept. So similarly with 44 and 131, and moving to this level, we have 11 here, which have 131 and 44 as its children. So now we will heapify it. 11, 130, 131 and 44. What we will do? Check this both. Which is greater? 131. Is it greater than the root? Yes. So replace this and this. 131 and 11. This is your answer. Okay, this set is done. Then 111 and 93 is fine. Considering this is a max heap, they have explicitly mentioned it is a max heap. So this is done. And next, this is also done. 90, 75, 33. So we'll update the tree in regarding of this. So after 101, we get 131, 11, and 44. So now compare this level. 101 has these two children, and 131 is greater than both 101 and 111. So we swap these places. I can simply write 131 here and 101 here. Now again check this. Is it greater? Yes. So this is considered to be done. Okay. Next. Next we have to shift 131 here and 82 comes here because 131 is greater than 90 and 82. So no need to get into details for every single step. So here comes your 82 and here comes your 131. Then now check this. Is it sorted? Not at all. So which one do you replace? 111 is greater than both this and this. So swap it. 82, 93, 111. So now look at this. 82 is greater than 93? Not at all. We'll try this 93 and 82. So I think we got our answer. 131, 111 and 90. So that is option D, and that's what we get as an answer for this question. Okay. Considering next question. A priority queue is implemented using a max heap. Always see which heap, otherwise we confuse. Initial level order. Okay. 10, 8, 5, 3, and 2. Then we insert 1. Fine. Then we insert 7. Okay. What is the final level order traversal? So considering this is a max heap, we go the bottom up approach because it is efficient algorithm rather than a regular one. So yeah. Okay. So 2 doesn't have children, 2, 3 doesn't have children, 1, 7 doesn't have any children. So come to this level. 8, 3, 2. It is perfectly balanced. 5, 1, 7. This is not balanced. So replace. Here comes 7, here comes 5. And I think that's it because you don't have anything left. Here's 10, which is greater than 8 and 7, 8 greater than 3 and 2, 7 greater than 1 and 5. I have my answer. So final level order traversal will be 10, 8, 7, 3, 2, 1, 5. 10, 8, 7, 3, 2, 1, 5. Yeah, this is our answer. So as simple as that. Which one of the following arrays represent a valid binary max heap? So we will see it in two approaches. For gate examination, for any kind of competitive examination where there is a heap question, you can directly look through that and answer that, and we will confirm that by drawing a tree again. So approach number one, by looking. So how can you do by just looking? So max heap. So consider a max heap. If you draw this 25, left 12, right 16, and to the left of 12 you will have 13. Will it be considered as a max heap? No. So this is not valid max heap. And then coming to this 25, 14 to the left, 13 to the right, and then 16 to the left of 14. Is it max heap? Never. Then 25. 25 to the 25, 14 to the left and 16 to the right, and we have 13 which is less than 14 to the left and 10 to the right. So these two are done. Then for 16, 8 is lesser and 12 is lesser, so this is perfectly valid. Let us take option 4 also. 25, 14 to the left, 12 to the right, 13 satisfied, 10 satisfied, 8 satisfied, but 16 not satisfied. For the 12th right, we'll get 16. Now we'll check this by drawing trees. I know it's a time waste. I mean, I'll not consider it as time waste. I know it's a huge process, but let us consider drawing that for clarity. I'll make it very quick. So here there is a contradicting statement. This is not a valid binary heap. And then 25, 14, 13, okay, again 16. This is not valid. Again 14, 16, this is valid. 13, 10, this is also valid. And then 8 and 12. So it is a complete valid binary tree. So there is no need of doing option 4 right now because we got our answer, which is option C. Then the correct answer to the Q3 is used an initial heap. Oh, the correct answer to the Q3, 25, 14, 16, 25, 14, 16, 13, 10, 8, 12. As per my memory, it's that 13, 10, 8, 12. Yeah, perfect. So after two delete max operation, what is the resulting array? Okay, fine. We have to delete the two maximum. So we have wiped off 25. In that place of 25, we have to place this part. So let's place that. 12 is placed here, and then we have to heapify this. Consider 14 and 16. 16 is greater than 12, so replace here 16 and here 12, perfectly balanced. And then you have to wipe off 16. For that you have to wipe off here 8 and put it here, and then Heapify it 14, 8. No, it's not there. So put up 14 here because it is greater than both 12 and 8, and put up 8 here. 8 is no less than 13 and both 10, but 13 is greater than 10. Hence we get 13 and 8. Resulting array 14, 13, 12, 8, 10. 14, 13, 12, 8, 10. This is our right option. That's it, as simple as that. Which statement is true? Heap sort is stable. Let's consider a heap sort. Let's consider an array. Suppose 8, 7, 5, 12, 11. 8, 7, 5, 12, 11. So if we want to find a min heap here, will it be stable? Of course not. See, whether you construct a binary tree, binary search tree, after the level of construction, if I want to construct this as a binary search tree, what I'll do? 8, 7 is less than, and 5 is less than 7, and then 12 is greater. So this is the tree. And for any of the operations, I will not reorder this tree. It is stable like this throughout the session. But what happens with the heap? It may be min heap or max heap, don't matter. If I want to get a min heap, I have to get this here, right? So this is why we say heap sort is not stable. So this option is eliminated. Build heap always takes order of log n log n. So this is partially correct. Let's understand with an example. If we take 1, 8, 4, 3, something like this, and 1, 8, 4, and 3. See, if we consider building it like this, suppose we want to build a max heap. If I want to build like this 1, 8, then it immediately converts to 8, 1. Hmm? Then you have 4, 8, 1, 4, and you have 3. So this whole process takes n log n. That's perfectly fine. But there is another thing called bottom up approach, which we have done in the earlier questions. So with that, what happens is this same 1843 becomes like this, and then we will heapify in this. So 3 has no children, so 3 is perfect. 8 has one child and it is greater, so no problem. 4 has no children, no problem. Then 1 has 8 and 4. 8 is greater than both this. So we will replace this by 8 and 1. So this algorithm takes order of n. So build heap can take order of n log n, but always is a wrong assumption. So we have to eliminate this option. And then bottom up build heaps run in order of n. I have just now told you bottom up heap 1, 8, 4, and 3. Same process, shift. It takes order of n times. That's it. Heapify for one node runs in order of n. See, if I'm doing this sort, I'm swapping 8 with 1 and 1 with 8. So for this one operation, it is order of 1 time, not order of n. The whole process of doing this is order of n. See, here I only did one, but if I have something like this 1, 2, 3, 4, 5, 6, and here I have 8, I have to do many operations. I have to do n operations. So this is not always like order of n. It can be one, but for one node it is strictly order of one. So the option D is also a wrong option. So we got our correct answer, which is option C. Here comes the main part of the movie. So a max heap contains 255 elements. Okay, let's construct it. Do you think I'm mad? No. So first of all, we have to find the height of it. So always remember. So instead of writing the pre-existing formulas, we will invent some formulas. We'll discover some formulas based on the level of the tree, not height of the tree. The all formulas are based on height centered. So I'm not saying you have to follow one approach. That's your wish. Level approach, I want to follow it and I want to teach that too. So there's nothing right and there's nothing wrong. As you, if you get the answer, then that's the right, just like that. So I'm considering this tree random value stuff. So if I have to find the height of this tree, what I'll do? This is 1, this is 2, this is 3. So there are 3 levels. Height is equals to level minus 1. Then my height becomes 2. Or else the height can be measured as this. This is 1 edge. This is 2 edge. The maximum number of edge to a root to a leaf. So what it becomes, that it is 2. So height is 2. We can follow both the ways. So for this I have drawn. But what to do for 255 elements? So this is where we invent the formulae, or we use the pre-existing formulae, but to understanding we discover that. So what we are gonna do is we are gonna create a pattern such that we can repeat to n number of nodes. So right here, how many nodes are there? 1, 2, 3, 4, 5, 6, 7. So there are 7 nodes right there. And if we observe this, this is 1, this is 2, and this is 3. So can we write this as 2 cube minus 1? So I'm with considering the levels, 2 power L minus 1 nodes. It has 2 power L minus 1 nodes. And for 2 power L minus 1 nodes, it has L minus 1 edges, or the height will be L minus 1. Am I right? Definitely. Let's see. So 3 minus 1. What is the height? 2. Okay. Now I'll erase all of this. I hope you understand the concept. Now we are gonna do it for 255 notes. Let that sink in. Okay. So 2 power 5 32, 2 power 6 64, 2 power 7 128, and then 2 power 8 is 256. Then 2 power 8 minus 1 notes. So 255 means 2 power 8 minus 1 notes. So for every 2 power L minus 1 nodes, the height will be L minus 1. So if you want to find out the height, you will get it as 8 minus 1, which is 7. So the answer for this is 7. And then number of leaves. We will discover a formula for that too. So if we consider this tree, we have 4 leaves. That means for 2 power 3 minus 1 node, there are 4 leaves, which means, can we consider it as uh, 2 power L minus 1 nodes? See, 4 is 2 square. If I want to consider this tree without this up to here, if these two are leaf nodes, then it will be 2 power 2 minus 1, right? So levels are 2, and 2 power 2 minus 1 is 2 power 1, which is considered as 2. I have 2 leaves here. So I hope you understand. So this is what the formula we are inventing. So for 2 power L minus 1 nodes again, the number of leaves you get is 2 power L minus 1, the power of L minus 1. So for 2 power 8 minus 1 nodes, you get number of leaves as 2 power 7, which is nothing but 128. So number of leaves is 128. And index of last internal node. So this one is a bit not tricky actually, but we can get multiple answers. So here they have clearly mentioned 0 based. I'll show you both cases. What if it is 1 based and what if it is 0 based? So index of the last internal node, nothing but for 2 power L minus 1 node, for 2 power 3 minus 1 nodes here, the last internal node gets to be this L is there, L which is 3 minus 1, which is 2. Am I right? So is this index correct? So let's consider this is zeroth index, the 0 base, zeroth index, first index, second index. So we can consider direct L minus 1. So we can the same formula L minus 1. And what if it is 1 based? It is simply L. It is simply the level which is it. Because if it is 1 based, then 1, 2, 3. So what this become? Just the level, right? So for this, For 2 power L minus 1 nodes, if you want to get the last internal nodes index, which is 0 based, you can simply write an L minus 1. Or if you want 1 based, it is L. So kindly note this. This is gonna save you lots of time. I mean, there are already pre-existing formulas, but we want to know why those formulas came into existence. So, okay, we didn't solve it yet, right? So, 7 minus 1, which is 6. Wait, what? Index of the last internal node. Who? Index of the last internal node. I have to consider more trees now because this has been too obvious right now because it is the third node and we get two that doesn't sync. So we make mistakes. Yeah, I didn't prepare for this. I'm doing right with you guys. Mistake do happen. Fine. I did a mistake, guys. Let's recover from it. So last internal node, right? So now it has 2 power 4 minus 1. So 4 minus 1. What the heck? That's not how it works. I did a filthy mistake, guys. Very cheap, very cheap. This is extremely wrong. Okay. For 2 power 4 minus 1 nodes, what will be the last 1, 2, sorry, 0, 1, 2, 3, 4, 5, 6. So the answer we need to get is 6. So let's focus on how can we get 6 first. Uh, 2 power 4 minus 1 nodes. And let's start with small. So for 2 power 3 minus 1, what I did here, 7 nodes. What if uh what if we can minus the see, what if we subtract the number of leaf nodes, right. See, the number of leaf nodes here is 4, and if I subtract that we get 3, which is 1 based. For 1 based, then we'll simply do minus 1 for that. Okay, I mean, this is not an efficient one, but let's do it for now. So if I do 2 power 4 minus 1, and the formula for this is 2 power 4 minus 1, which is 2 cube minus 2 cube. So if I have these nodes, I mean 8 nodes here, minus 8, and this is like 7 plus 8, 15. 15 minus 8, I get 7. 1, 2, 3, 4, 5, 6, 7. This is 1 based. So minus 1. So it is 2 power minus 1 minus 2 power L minus 1 minus 1. So simply I can write 2 power L minus 2 power L minus 1 minus 2. Or if we want to take out common, 2 power L of 2 minus uh, 2 power 2 power oh 1 by okay, let's just do it this way. Let's just do it this way. 2 power L minus 2 power L minus 1 minus 2 to get the 0th index. So now 2 power we got 8 here. 2 power 8 minus uh, 2 power 7 minus 2. Okay. 2 power 8 is 64. Sorry, we 255. 2 power, yeah, what I'm doing here. 2 power 8 is 256 minus 128 minus 2. 256 minus 128 is 128. 128 minus, So we can do one thing, right? We can do something. We can half it and do it, right? We can find another approach. Wait, this is so long to remember. So what if I did 2 power 4 by 2? No, 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 no. Wait. By 2 minus 2. So what I'll get? 2 cube. 2 cube minus 2 is uh 2, sorry, 2 cube minus 2, which I'll get 6. So 0, 1, 2, 3, 4, 5, 6. Yeah, this is very good. This is very good actually. This is very good. This is extremely good. All forget all this rubbish. We got a new one, efficient one. So we are gonna do 2 power 8 by 2 minus 2, which will get 2 power 7, which is 128 minus 2, 126. Same answer we'll get with that formula too. Okay, this is cool. This is cool. Let's experiment on this. This is 2 cube, right? 2 cube by 2 minus 2. 2 square minus 2, 3. Wait, 2 square, 4 minus 2, 2, sorry, 0, 1, 2. With 0 index, we have to do minus 2. And with 1 index, we have to do minus 1. That's the only difference. Okay, we took a lot of time in this. But I'm happy. A node is at depth k in a heap of height h. Okay, we're going to next question. The worst case heapify down time complexity is. Let's do it. Let's consider some nodes here. Okay. So worst case time complexity, we consider it as a max heap, and here is the maximum element out of all this. So within so heapify down complexity, for getting that, I wanna tell something, because we have done it very long time. I mean many times. See, in the heapify down, you will first traverse only this. I mean, first do only this part. It has no children, it has no children. So we leave this leaf nodes. When coming to the internal nodes, we are doing in the specific height of this. So a node is at k depth and a height of h. So consider, if we consider this one, so until from the in the height of h and until depth of k, so we get the worst case time complexity of swapping these two. It will be order of h minus k. So if you think there is a root node and there is something, and if you do this, this is the h, this is the k. So it will be order of h minus k, and everyone else will not order of k. It is does see at a depth k. See, if I have like this element and I have uh, like something like this, and this is my k. So based on this, I cannot determine how much is it. Of course, see, if we do this, we get order of n. Either we get order of 2 and this is order of n. But but this is not an way, this is not an answer, this is not a time complexity that we simply get. How will you get it? Based on this, which height are you comparing? So that is very important. And log h, of course not, because even in the normal complexity, we will get a bare minimum of order of n log n and an order of n which is most efficient. So log h, nothing doing. Order of n, yes, but within provided a specific height, we will get it order of h minus k and not order of n this time. See, if we consider the overall time complexity, then it will be order of n from the bottom of approach. But when there is something like a height and k given separately to you, you have to adjust according to the constraints. So this is also a wrong answer here, because we are overall we are considering, but in the two we are following some approach which gives us the intermediate height and k. So in this you get height h minus k, and in this also you get h minus k. H is here and k is here. You will get h minus k. That's it. Next, which statement is false? Every heap is a complete binary tree. Of course, yes. False. Acha, this is true. Every complete binary tree is a heap. No, we got our answer. Let's check others too. Max heap supports efficient priority queue operations. Yeah, without priority queue it is order of n, and with priority queue it is order of log n, like operations like searching or finding maximum or minimum element. Because we can check it is max it is minimum, then heapify. For heapifying we'll get some time, and through that we can find it. So complete binary tree is a heap there. So this is also a right option. Root of max heap store the maximum. Of course, if you consider this as a max heap, let's do 8, 4, and 3. If we get 4 in here, we'll swap and do it max heap. So if we consider something to be a max heap, then of course it will store root element. That's it. Okay. Of course, I'll not construct it. Max heap has 1023 nodes. This is why the formula deriving part was so time taking, and it is so important. So uh, we have to determine this height, number of internal nodes, number of leaves, and maximum swaps during one heapify down. What? One heapify down. Okay, we got a new one and we'll derive it. First we'll do this height. So what we discussed about height, for 2 power l minus 1 nodes, l minus 1 is the height. And internal nodes, number of internal nodes. Okay, that gives us to one based, because number of internal nodes is nothing but the one based index. Suppose if we consider something like this, 1, 2, 3. 3 is the last index node for this, and number of nodes is also 3. So if we consider a one based index, that is minus 1, we can get that through. So which is 2 power uh, some L by 2 power L minus 1 minus 1 for getting number of internal nodes. Number of leaves, what we have done to leaves? 2 power L minus 1, right? Yeah, 2 power L minus 1. Let me just confirm. 2 power 2 minus 1. Hmm? 2 power 2, 4 minus 1, 3. No, that gets the whole total. 2 power L minus 1 minus 1, I guess so. Yeah, 2 power L minus 1 minus 1, which gives 2 power here. This is 2 power 2 minus 1. Wait, what? No, why am this confused? 2 power 2 minus 1. Eh, hell with me, bro. 2 power L, that's it. 2 power 2. 2 power 2 minus 1. 2 power 1, which is 2. Yeah, 2 power L minus 1. Correct? I'm getting confused. 2 power L minus 1 is the answer, guys. 2 power L minus 1. Yeah. 2 power 2 minus 1, 2 square minus 1, 4 minus 1, which is 3. Eh, what rubbish. 2 power 2 minus 1, which is power 1, which is 2. Sorry. So for 1023, previously we got 2 power 8 as 256. 2 power 9 is 512, and 2 power 10 is 1023. So we get 2 power 10 minus 1. For 2 power 10 minus 1, the height will be 10 minus 1, which is 9. The answer is 9. And then next coming to the number of internal nodes. So 2 power 10 by 2 power 9 minus 1. Wait, what? Sorry. Here just random 2, that's it. Normal 2. So 2 power 9, and we get what we'll get. 2 power 9 means 512 minus 1. 511 nodes. 511 root leaf nodes. No, internal nodes, sorry. 511 internal nodes. Then subtract, just subtract, bro. 511 from 1023. 1023, 511, 2, 2, 5. 522. Wait, what? Sorry. 2 minus 1 is 1. 5 and 2. So, as I said, 2 power L minus 1, which is 2 power 9, which we get 5 and 2 again. So, that's it. This one gets me a little bit confusing, and honestly, I think I don't know the answer for that. But let's do it. Maximum swaps during one heapify down. Oh, maximum swaps. So we consider a tree which is very big. We consider a big tree to get a better answer. So I have to swap this 3 and it has levels 1, 2, 3 and 4. So for 4 levels, maximum swap during one heapify down. So uh, for one heapify down, bro, how can we guarantee it? It depends on the values of the above thing, right? Suppose if I something 8 to uh 5, some 1, 3, 4, 6. So if I gotta get through this, I have to swap here and then I will swap here. This is fine. But what if I have uh wait a minute. Mm, I'm not getting this. Okay, I'll upload a short video based on just explaining this. Right now, I'm not getting it. I'll look through some ChatGPT or something and learn this, and I'll update you later. I'll definitely do that. Alright, next. Can a max heap contain the following parent-child relationship? Parent, it is 450. Child, it is 900. Bro, no. That's a straight no because to have a parent child relationship you need to at least have 450 in this case child as child because at the parent and child must have the values greater than or equal to them. Parent must be greater than or equal to child. So this is my one line answer. So that's the end of the video, guys. So there will be more videos coming soon, and I'll definitely make sure that this ninth one will come. I mean, I'll upload a short based on this because right now I'm not getting through the logic and I cannot waste the time by thinking it right now. So, thank you for watching. I hope you learned something new. Thank you.